Okay. So, hi everyone. My name is Josué Moreau. I come from Inria and University Paris-Saclay. And I'm going to talk to you about a safe language, a safe low-level language for computer algebra, and its formally verified compiler. So to begin with, a lot of computer algebra systems use a few specialized libraries, such as GMP for operations or arbitrary large integers, or BLAS for operations or vectors or matrices. And even these libraries are heavily used. They still have some bugs. So for instance, in this version of GMP, there was an error in the modular exponentiation implementation if the divider was over 15,000 decimals. And so this kind of bugs is very tricky to find, and therefore we want to prove that these implementations are correct. And even if it's the case, even if we manage to prove such programs, we can still have bugs which can be introduced by the compiler, leading to crashes and miscomputations. So the current implementations of these libraries are written in C and Fortran. This is good because these languages do not get in the way of the user. They let him write the program as in the way he wants, and also they provide highly optimized compilers. But these languages are not safe, so we cannot ensure that non-defined behavior happen. And also, the program verification is often difficult because their semantics is not well suited for program verification. So this adds some difficulty to proofs that are already mathematically difficult. And also, these compilers, as they are very optimizing, are too complicated for total confidence in the generated code. So to tackle these problems, we want a language dedicated to writing such specialized libraries. We want it to be safe and also to provide the semantics which help doing proof of programs. We also want a compiler formally verified with CoC. That is, we want to prove that the semantics is preserved during the whole compilation passes, and also that this language is type safe and that its type checker is correct. So firstly, I'm going to talk about such a language and its semantics, then about the compiler, and finally about formal verification of the properties I just stated before. So the first thing we want in such a language is some kind of expressiveness in the signature of functions. So if you look at this example, this is the dot product function from BLAS. This is written in Fortran. And you can see that here there is no explicit relation between the arrays, which are ZX and ZY, and their sizes, which are expressed using n inx and y. And you have to look at the documentation to see that, OK, the size of ZX is 1 plus n minus 1 times the absolute value of inx. But this is not clear in the program, and therefore, the semantics doesn't ensure that when you call this function, you correctly call it. And on the side of GMP, another kind of property we will want is some kind of non-overlapping property on some arrays. For instance, in this square function from GMP, RP and S1P don't overlap. So let's take an example in our language. So this is the naive matrix multiplication, and a few things can be noted here. The first one is that the sizes are explicit. They are passed as parameters because this is the style of BLAS and the MPN layer of GMP. Also, we can share these sizes across multiple arrays, and we have some kind of distinction between mutable and persistent arrays with borrowing. So we can see that, for instance, here, A here is a matrix of 64-bit integers signed, and that its size is m times n. And finally, about array accesses. So if you access outside the bounds of an array, this is not a defined behavior. This is a runtime error, so there are dynamic checks which ensure that you access in the bounds, and if it's not the case, the program execution stops. So now we did the same decision, the same decision as what it's done in something like Rust. So we say that we forbid aliasing between mutable arrays and any other array. So this is good because we can have a copy restore semantics, so we have no global memory, no location-based memory. We only have a local environment, and we have deep copies of arrays between the function, between the calling function and the call function, at function call and return. And also, because we forbid this aliasing, we can efficiently translate these semantics into a pointer-based into pointers. So we can use on lower level language pointers instead of these costly deep copies. And also this adds some expressiveness in the signatures because we can trivially state that non-mutable variables aren't modified if you don't directly write in them. And finally, we don't need any separation logic. So this is good for program verification because it's often very complicated. So now let's take an overview of some semantic rules. So we have values, for instance, integers, and we have arrays. And in the arrays, we don't have any location, any position in a memory because we don't have any memory. So this is just the list of the values which are the content of this array. And for the assignment rule, you can see that here we just write in the local environment the value. So we evaluate the path where we want to write, we evaluate the expression we want to write, and we write this value at the evaluated path. For dynamic allocation, this is the same, except that here we have to initialize the array, and we add it to the local environment. For freeing, we just remove it from the local environment. And for function return, you can see that here, so here we say that we return from a function whose environment was EF, and we return to a function whose environment is E, and we use this, so this is the copy restore mechanism, so we copy the arrays, the modified values of the array in the called function to the paths which were passed as argument for mutable arrays from the calling function. So now, about the compiler. So the language I showed you before, we name it Kapla. And the first thing we do is to translate it to another language, which is L1. So L1 is the first language of our formally verified compiler. And it doesn't have any unified behavior. And the only thing we do for this pass is type inference and some simplifications on the program. Then we translate it to assembly, and to do this, we translate it to the C# intermediate language of CompCert, and then we let CompCert translate it to assembly. So this language, C# uses classic C semantics, so it's a pointer it uses pointers and locations. And to translate from L1 to C#, we added another language, which is L2. So L2 has undefined behaviors. And so to be clear, L1 don't have any defined behavior. So accessing outside the bounds of an array, it's not an undefined behavior. And for L2 it is. So to ensure that these undefined behavior don't happen and that the semantics preserved, we add dynamic tests in this translation. So these are just assertions before the array access. And because sometimes performance is more important than guarantees on the generated code, we have an unverified C backend. So during this translation, we add some annotations on the program, such as the restrict keyword, so that compilers such as GC or Clang can generate efficient code. So now for the performance, for the benchmark. So we implemented a subset of functions from BLAS and GMP. So these are the functions from BLAS, and the last one is from GMP. And you can see that here, so this is the fully verified toolchain. And you can see that the results are not very good, but these are not as bad as, these are not really bad because this is a fully verified toolchain. And we can have better performance by using the unverified C backend. So by using GCC on LLVM, we have way better performance. And we can even go further by adding some assertions in our source code. And these assertions help GMP and LLVM remove even more assertions in the loops so that they can vectorize. Oh, sorry, I forgot to say, so these numbers are ratios of our execution time of our implementation upon the execution time of the reference implementation from BLAS and GMP. And these implementations, reference implementations, are not optimized for a specific kind of processor. That's just x86-64 implementations. So now, about the formal verification. So property we prove for formally verified compiler here is forward simulation. So we prove that each step in CAPLA implies a sequence of no undefined behavior steps in the assembly, and that some kind of relation is preserved during the whole execution, and that this relation does the correspondence between our memory model and the CompCert memory model. So the difficulty of this proof is comes from the fact that we don't have the same memory model as CompCert. We have only local environments, while CompCert uses 4 C# minor locations and memory and stack and all of that. In fact, often the property we want to prove is backward simulation, and this is the kind of property that is proved in CompCert, but our language is deterministic, so forward simulation implies backward simulation. And for type safety, we prove the classic property of type safety. So the invariance, this is just a subset of invariance. We have more invariance, especially about the tracking of some undefined variables. But the main invariants are the classic one for a typed language, and also we have that an invariant on sizes of arrays. So we say that the evaluated sizes of the arrays are at most the actual size of the array in the environment. And we prove that these invariants are preserved during the whole execution, and also that with a non-final state they imply a new step in the semantics, the progress. So to conclude, we now have a safe language for computer algebra, which is suitable for array-based programs and which has a non-aliasing policy for mutable memory. This is the same kind of property that is ensured in Rust. And also we have a simple semantics, which we expect will simplify program reasoning. We also have a correctness proof and the formalization of our semantics, and so the correctness of the compiler and the safety proofs, which were implemented and verified with the coq proof assistant. So this represents some lines of proofs and code. And also we have an unverified C backend for cases where performance is more important than guarantees on the generated code. And about the future, we want to extend our language with views so that we can have some kind of pointer arithmetic. We also want to define program logic for program verification, and also add some compiler optimizations, such as removing automatically some assertions in the code that are generated for array accesses, for instance. In some case, we can a simple linear arithmetic decision procedure could eliminate them. And so to finish, this work is part of the Fresco projects, which aims at turning the coq proof assistant into a computer algebra system. So thank you for your attention.
Hello, Adam Chapala from the MIT. Your performance comparisons always took as a baseline using existing C compilers. Yep. And we found that for some algorithms in this general space, for instance, where you have arrays whose lengths are known at compile time, you can often get a factor of 2 or more of better performance by handwriting assembly or just compiling in a very different way than GCC and Clang do. Do you have any comparisons against best known assembly code for the kinds of programs that you're working with here?
In this case, for BLAS, this is just the reference implementation. So this is not. We didn't try it with more optimizing implementations, which were written in assembly. For GMP, we did try. So this is this implementation is it's assembly, but it's not fine-tuned for a specific model of processor. And we tried with fine-tuned the fine-tuned version of this function, and it's something about 180 with GCC and VM. I don't remember exactly the number, but it's of the same kind of number. So yeah, so we cannot. In fact, we cannot. The goal here is, as we want to turn the conc proof assistant into a formally verified, into a computer algebra system. The fact is not to have the same kind of performance as the most optimized implementations, but we consider that a factor of 2 is acceptable.
Thank you.
Okay. Hello, Algebra. Thank you for the talk. So you are proposing here to basically have a language which is meant to implement functionality which is then accessed by FFI, right? So the host language can then call your functions and can violate the types that the signatures that you have assigned to them, right? So like, what are your thoughts on ensuring that this does not happen?
Okay. So yeah, so that's something we have to prove. We have to so. Okay, so we could have some, I don't know, some checks before for external calls. I don't know, some wrapper which checks that the invariants are correct. So this is, of course, we want to call these functions from outside. So yeah, it's we will have to check that these invariants are verified. But now currently I don't know what is the best way of doing this, but yeah, maybe checking in the source language or checking in the destination language or in this language.
Okay, great, thank you.
Hi, thank you for the talk. I was wondering about the impact of dynamic checks, and if they do have an impact, are you trying to do something smart like putting them outside of loops, or just removing them if you prove a specification, or if they don't impact performances?
Oh, okay. So these assertions have an important impact. So you can see that, in fact, here adding assertions. In fact, this is just some equality of nonlinear arithmetic that GCC or Clang are not able to do. So we add these assertions. We know that they are correct, and we add them at the beginning of the function. But the fact here is that assertions have huge impact, because if compilers are not able to remove them, they cannot, for instance, vectorize. So removing at most as we can at most assertions as we can is good, because we can help the compilers. And currently, these assertions are added manually, but we currently don't really know how to automatically add them.
Okay, yeah, thank you.
Thanks very much.